Hi everyone, welcome back. In the previous video we learned about big O notation or time complexity. We defined big O notation as a way of describing the complexity of an algorithm or the running time of an algorithm. It is used to measure how an algorithm runtime changes as the size of its input data increases. So one thing to mention, beside measuring algorithms running time, big O notation is also used to measure the space or memory requirement for your program or algorithm as the input data size grows. But in this lesson, we are not going to talk about the space complexity of an algorithm. We'll be only talking about time complexity or running time of an algorithm. So big O notation is also known as a way of expressing the asymptotic behavior of an algorithm. This means that it describes how the algorithm behaves as the input size or input data size gets larger and larger. So in the previous video, we saw an example of constant time complexity. We saw linear time complexity or big O of n. So in this video, we'll talk more about big O notations and time complexities of different algorithms. We will learn about logarithmic time complexity or big O of log n. We will talk about quadratic time complexity and polynomial time complexities or cubic time complexity. So essentially these big O notation concepts provides a method to describe how the time required to run a function or algorithm increases as the size of its input data increases or expands very large. An important aspect of the time complexity and big O notation is that it remains independent of a specific computing environment in which the algorithm or the function operates. This implies that algorithms execution time may vary between different hardware environments. For instance, a newer computer and an older computer may indeed demonstrate different running speeds. Definitely, the older computer may take slightly more time to execute the same algorithm and compared to a newer or faster computer. However, the time complexity of an algorithm, whether it is linear time or big O of n, or it is a constant time, or it is a logarithmic time, it remains the same and it doesn't change as we change the environment or computer. Now, the primary reason for utilizing mathematical notation like big O of n or big O of log n to express the time complexity of an algorithm is the significant variation in execution time based on the computer or the system being used. For instance, a slower computer may complete the same algorithm or the same task in 5 milliseconds, while a faster computer or a system could accomplish the same task or algorithm in 2 milliseconds. Hence, measuring the running time of an algorithm in absolute terms such as seconds or milliseconds prove ineffective, or it doesn't make sense saying my algorithm running time is 1 millisecond or it is 2 milliseconds because running the same function or algorithm in different system may give larger or smaller running time depending on the speed of the underlying system or computer. It also depends on the type of processor being used or how many other programs or applications are open while we run the same program. So it doesn't make sense to say the running time of this algorithm is this much of seconds or this much of milliseconds. A more meaningful approach involves mathematical representing the time complexity known as big O notation in computer science. And instead of specifying the algorithm running time in 2 seconds or 5 seconds, we employ big O notation to denote the time complexity of an algorithm. Remember, these concepts are language agnostic. The principle of big O notation applies across all the programming languages, regardless of the computer you use or the speed of the computer or the programming language you are using. The algorithm or the sequence of steps to solve a problem remains the same, and thus the time complexity as denoted by big O notation remains the same across all different platforms as long as the same steps are used or the same algorithm is used to solve the given problem. This consistency makes big O notation a powerful tool for understanding the scalability and efficiency of our algorithm. So let me show you. I have written some code here. Let me go to my IDE. I have created a function, create array. So this function returns an integer array. It takes an integer size. So first we create an array of that size. Then we loop from 0 up to that the given size and store 1 up to size to that array. So for the first element, we'll store 1, 2, 3, 4, 5 up to size. So we know this function we use, one for loop, is linear, has a linear time complexity or big O of n. So the number of steps or time taken to execute this function is directly proportional to the amount of size we pass in our function. Then I have created another array, another function that returns an array of integer called create random array. This also takes an integer size. What I have done is using the random class, I have created a random object. So I also created an array of that size. This time, instead of storing contiguous numbers 1, 2, 3, 4, 5 up to size, this time I store random numbers in the index location, ith index location. So the random object has a next function. This next function returns a random integer that is within the specified range. So in this case, I want to generate random numbers between 1 to 1000 each time and store it in array of I. Then I return the array. Then I have a print function that takes an array of integer numbers. It loops through each element of array and just print the item or each element. As we know, this function also has a running time of big O of n or linear time. So the running time of this function is directly proportional to the size of the array we pass. So let's take a look here. I have called the function create array to create an array of, say, I want to create an array of size 10 numbers, 1 up to 10, and store it in this array 1. Then I used a stopwatch class. This stopwatch class basically provides a set of methods and properties that we can use to accurately measure the elapsed time. So using this function, this object, we can access the start function to start counting the time. Then between the start and the stop function, we can execute our algorithm to measure how much time it takes. In this case, I am going to call my print algorithm or print function. Then here, using the stopwatch.elapse property, as we can see, it returns a time span. We can calculate the time between starting and also ending. As this returns a time span, I have created a time span object and store the value in time span. So using this time span or TS object, we can access the number of hours, minutes, or seconds or milliseconds, and I'm going to print it in this format. So this is denoting the number of hours, number of minutes, seconds, and milliseconds. We can also use the stopwatch elapse milliseconds property to get the number of milliseconds, or we can also use the elapsed total seconds to get elapsed time in seconds and also get elapsed times in minute. So let me execute my algorithm or function with size 10 and see how much time it takes. It takes 15 milliseconds. If I run it again, we can see at this time we got 14 milliseconds. If I increase the number of elements, say I want to increase it to 100 or say 1000, so the time taken should also increase. This time the algorithm took 86 milliseconds. If I run it again with 1000 numbers, so at this time we got 87. Each time we run the algorithm, we get different time because it depends on the number of applications opened in our computer or the processor we use or how fast or slow our computer is. That's why it's not a good idea to represent the running time of an algorithm in absolute values such as number of seconds, because each time we run that we get different values. We cannot get, like this time we got it faster, 84 milliseconds. So that's why we use mathematical notation or functions to represent the big O notation. We also saw the graph of a linear time complexity or big O of n. It depends on, it's directly proportional to the number of elements we pass to our functions. Say if I want to show you how many steps are presented here, so let me define an integer variable int static int number of steps. Let's initialize it to 0. If I increment this number of steps in my this algorithm or function, number of steps plus plus, and here I want to print the number of steps here, number of steps. We can see for 1000 elements, so we require 1000 steps. If I increase it make it double, so the number of step requires to execute this function doubles 2000. That's why for a linear time complexity, for each input size we increase in our input data, the number of CPU operation or number of operations required to execute the algorithm increases proportionally. Now let's take a look at rules for simplifying the big O notation. So the first rule is we always analyze the worst case scenario. Big O notation is often used to describe the worst case performance of an algorithm. This means that the analysis focuses on the maximum number of operations that might be required regardless of the size of input data. In other words, big O notation encapsulates the upper bound of the time complexity, giving us an understanding of how the execution time might grow in most unfavorable situations. If we take an example here, let me go to IDE. So say we have a function or algorithm find item that takes an array of integer, and also it takes an integer value or item. What it's going to do, it will search or loop through each element of array, and it will return true if the item is found, otherwise it will return false. Okay, so if we have this array, let me copy this array. Say I have an array of 8 elements. I want to search for item. If my item is 1, so this is going to be the best case scenario. We can find element 1 in one operation, so we start looping from beginning of array. For array of 0, we can check if array of 0 equal to item. That is, so we just return true. So this is going to take a constant time or big O of 1. This is going to be the best case scenario in our algorithm. But what if we want to search for an item at the middle of array? Say I want to search for 5 or 4. So if I want to search for 4, I start looping from beginning of array and going all the way. Once I reach index 3, I find 4. And in this case, I can find the element in big O of n by 2, for example. This is going to be an average case scenario. But what if the user want to search for item 8, which is the end of the array? So we start looping from the beginning and going all the way to the end of array, looping n times. So once we reach the end of array, we found the item and we return true. In that case, our algorithm takes big O of n, or n times we loop. So this is going to be the worst case scenario, or the worst case scenario could be if the user want to search for an item that's not present in our array. Say the user want to search for item 10. What we are going to do in that case, we start looping from the beginning of array. Once we reach at the end of array, we didn't find the algorithm or the item, so we return false. In that case, we also have big O of n, or worst time complexity. That's why the first rule is we always take the worst case scenario, not the best case or the average case. So this function has a running time of big O of n, or linear time complexity. Or say I have another function, find maximum, that takes an array of integer. So what it's going to do is going to loop through each element of the array and find the maximum value in the array. What I've done is I have defined an integer variable called max and assign it to minimum value. So I loop through each element of array and check if array of I greater than max. If that is so, I'm going to update my max. Else, we just keep looping. So in the worst case scenario, this function is also going to have a big O of n, or linear time complexity. And then the second rule we have, ignore constant factors or drop the coefficient of the fastest growing term. Then we have differentiate term for separate inputs. We have also drop non-dominant term. So we are going to take a look at each one of these rules, example of each one of these rules. So The second one is ignore the constant factor. In big O notation, constants are ignored because they do not significantly affect the growth rate of the function as the input size increases. So say I have this function or algorithm process array 2 times. So this is going to take an array of integer and it is going to loop through elements of array 2 times. So I will have big O of n, since it is going to loop through elements of the array n times, and also this for loop is also going to have a big O of n, since it's also iterating n times through each element of the array, because we are starting from zero going all the way to end of the array. So these both loop functions, for loops, have big O of n. So to calculate the time complexity of this function or this algorithm, we have big O of 2n. So we will have big O of n plus n, since we have 2 for loops. This is going to result to big O of 2n. So the second rule is to drop the coefficient or constant times. So I'm going to drop that and the final time complexity of the algorithm is going to be big O of n. If we have big O of 3n or 4n or 100n, so this is also going to be equal to big O of n. We always drop the coefficient of the growing term. The fastest growing term in this case is n. We just keep the fastest growing term and drop the coefficient. Same case if we have another time complexity, say n plus 100 or a constant. So in that case also, if it is big O of n plus 100, we can simplify this time complexity to big O of n. We drop the constant terms. If we have, say, big O of n plus say 3n plus 1 million, or a long constant number, the rule is to drop the constant terms and also drop the coefficient. Only we keep the fastest growing term, because this will contribute enormously to the running time of an algorithm as the function input size grows. So this big O notation simplifies to big O of n, or linear time complexity. In this previous example, if we note here, so this is going to be a constant time complexity, or big O of 1. Big O of 1. This loops through each element of the array. So this is going to be a big O of n, since it is going to iterate through elements n times. If we take this one, this comparison is going to also be big O of 1. Big O of 1. This is also going to be big O of 1, or constant time. Big O of 1. And this return statement is also going to take constant time, or big O of 1. While calculating the overall time complexity of this function, so we might have 1, 2, 3, or 4. This goes n times, so we can multiply it by n. So we have like big O of n plus big O of, say, 2 or 3. So we can drop all the constant time complexities, and we only consider the fastest growing term, which is n. So the number of operations, these operations all depend on the number of elements in the array. As the number of elements of the array grows, these operations also grow proportionally. So that's why we always drop the constant times, and we only take in consideration the fastest growing term. In this case, it is big O of n, or linear time. If we consider this example, print odd elements or even elements, this takes array of integers. So first we check if array has two or more elements. So this is going to be a constant time. This is also going to be a constant time. This is going to be constant time. So this is a for loop. It loops n times, or iterate n times. This will have big O of n time complexity. So big O of n. So this is going to be the fastest growing term. So the number of operations is mainly dependent on this for loop, or big O of n, and we have constant time here, constant time here. While we calculate the overall time complexity of this function, so we drop all these constant time complexities and we take in consideration only this fastest growing term. So the third rule is differentiate term for separate inputs. If an algorithm takes multiple inputs, we use different variables to represent the size of the input in big O notation. For instance, if a function takes an array of integers and a string, we loop over the elements of the array and a string separately. We could represent this as big O of n plus m because we have two different input size. In this case, if we have two for loops after each other, and each for loop loops n times the same amount of time, so we can take only one, drop the coefficient and take only big O of n. But in the case we have two separate variables of input size, say we take an array of integers and a string, we don't know the length of the string and we don't know the length of the array. They might have different sizes, so we take different variables to calculate the time complexity of this type of functions. So using one for loop, I loop through elements of the array. So this might have, say, big O of n, where n is the length or the size of the array, and also I use another for loop to loop through the elements of the string. So since this has a different length, so I'm going to use a different variable, so I'm call it big O of m in this case. So to calculate the overall time complexity of this function, so we represent it as big O of n plus m. So this is going to be might be one of the interview questions to trick you guys. So in that case, if we have different variables or different input size, for each input size we take different values. Say if I take another array here, this function takes another array of int, say arr. In that case, what I'm going to do, I'm going to take three variables to calculate. If I loop through the elements of this array also, what I'm going to do, I'm going to take three separate variables. So the big O notation of this function in that case is going to be big O of n, which represents the size of the first array, plus m, which represents the size of the string, plus say z, which represents the size of the last array. We cannot represent this as size of 3n and finally drop the 3, so we cannot set big O of n. In that case, we say the time complexity of this function or algorithm is going to be big O of n plus m plus z, where this variable represents the size of different input to the function. So the fourth rule is drop non-dominant terms. We always keep only the fastest growing term while calculating the time complexity of an algorithm. We drop the less growing terms and only keep the fastest growing term. We also drop the constant terms. Say if I have a function like this, if I calculate the time complexity of an algorithm and I say get time equal to n squared plus n plus 3. So in that case, the fastest growing term is going to be the term having the highest degree. In this case, n squared is going to be the fastest growing term. So I'm going to drop the less fast growing term and also drop the constant. So in that case, the time complexity of this function is going to be big O of n squared or quadratic time complexity. Say I also have, if I get another function t equal to 3n cubed plus 4 n squared plus 1000 n plus million. So if I get a function like this, what I'm going to do is I will keep only the fastest growing term, which has the highest degree, and drop all the coefficients and all the non-fastest growing term and constant. So this is going to be the non-fastest growing term. This is also going to be dropped. This is also going to be dropped. So I will be left with 3n squared n cubed. So also rule number 1 was to drop the constants and also the coefficients. So in that case, I can drop 3 also. So the big O of this function is going to be big O of n cubed or cubic time complexity. If I take an example here, say I have a function, some function that takes an array. Using a for loop, I'm looping through each element of the array, and for each element of the array I use inner loop. So this is going to have big O of n or it iterates n times. The inner loop also iterates n times. So this is going to be big O of n, and this is also going to be big O of n, and this is going to be n also big O of n. So since these are nested loops, we are going to multiply these two time complexities. So this is going to be n into n is going to be n squared. But if we have two or more linear times or time complexities that come after each other, for example in this case, in that case we add these two time complexities. So in this case it will have big O of n plus big O of n, that will be big O of 2n. We drop the 2 and we will get big O of n. But in case of inner or nested loops, we multiply the linear time complexities. So in this case we will get big O of n into n. So we will get big O of n into, since we have nested loop, into big O of n, plus, since the last for loop or linear time is after this for loop, we use plus in this case. So plus big O of n. So this will be big O of n into n plus big O of n. This is going to be big O of n squared plus big O of n. So we are going to keep only the dominant term. In this case, n squared has higher degree, and we drop the non-dominant term. So we keep only big O of n squared. So to calculate the overall time complexity of this function, we will have big O of n squared, or quadratic time complexity in that case. This is also another example of, let's see what is the time complexity of this function. We have two inner loops, the outer loops n times, and the inner loop loops 10 times for each element of the array. So what do you guys think? What will be the time complexity of this function? So the time complexity of this function is going to be linear time complexity, where n is the size of the input data type, because the inner loop loops constant number of times. So it doesn't loop n times. So if the size of the array increases, it's not going to affect the number of iteration of this inner loop. So this is going to loop constant every time, but the outer loop only depends to the number of the array or the size of the array. So that's why we consider only this outer loop. So this is going to be big O of n, since it loops from 0 to end of the array, and as the size of the array increases, it's going to affect this outer loop. This inner loop is going to be big O of say it loops 10 times for each element, so we are going to take it big O of 10. So since these are nested loop, we are going to multiply them. We can take big O of n for the outer loop into big O of 10. So this is going to be big O of 10 n's. So the rule was we always drop the coefficient, so we get big O of n in that case. So here, even though we have nested loops, we get big O of n, or linear time complexity, for this function. So let me show you why we always consider the fastest growing term and we drop the less fastest growing term or constants, because the less fastest growing term or constant terms, they do not make a significant contribution to number of the operations required to execute the function as the number of input grows. Say I have n squared plus n, or big O of n squared, or order of n, plus big O of n, or linear time, plus say 1000. Okay, for input size of 2, so this term is going to be 4, and this term is going to be 2, and this term remains constant. For an input of say 100, this term is going to be 10,000, this term is going to be 100, and this is going to be 1000. Okay, these remains constant all the time, and this less growing term grows very less or insignificantly. But if I have an input size of 1000, so this fastest growing term is going to be 1 million operations, 1 million operations, and this second term, or n, is going to remain 1000, which is very less operation in compared to 1 million. and this is also going to remain constant 1000. So these two terms contributes very less or slightly to the number of operations required to execute the function or time taking to execute the function. That's why we always ignore these two these two terms and only consider the fastest growing term, in this case big O of n squared, while computing the time complexity of the function. Now that we got an idea about time complexity and big O notation and how to calculate some basic time complexities for a given function, we learn about constant time complexity, or a big O of 1, also denoted as big O of 1. It's basically a measure of an algorithm's efficiency where the time taken to execute the algorithm does not change with the size of the input dataset. In other words, no matter how big or large or small your input is, the operation will always take the same amount of time. In this case, this function takes an array and always perform one operation that returns, calculate and returns the first element of the array. If we pass it an array with 2 elements, it only executes one operation. If we pass an array with millions of elements, it still executes one operation or takes constant time to execute this function. Same case with this function. It takes a number and checks whether the number is even or odd. If it is even, it's going to return true, otherwise it is going to return false. If we consider this update element function, this takes a list of integer values, an index number, and a new value. So we are going to update the item at index location with this new value. First, we are going to check if the index value is a valid index value or not. If so, then we directly access the item at this index location and just assign it to a new value. So this also takes a constant time. No matter how big the list of number is, we just perform only one operation. So this also takes a constant time. Then we learn about linear time complexity. Basically, big O of n, or linear time complexity, is a measure of an algorithm's efficiency where the time taken to execute the operation grows proportionally with the size of the input dataset. In other words, if you double the size of the input, the algorithm will take approximately double time to complete the operation. So if we take a look at the graph of the linear time, we can see it grows proportionally as the input size grows. It takes that much number of CPU operations. So if we take a look at this function, it takes an array and returns the sum of all elements of the array. We loop through the elements of the array and we calculate the sum. So if we want to take a look at the number of operations, the increase in number of operations. So I have a class called big O notation, and inside this class we have different functions. So let me define a private int number of operations. First I'm gonna set it to 0, or we can set it to 0 in the constructor of this class. Then I'm going to define a public int get a number of operations. So this function just returns the number of operations. So in this function I'm going to increment the number of operations. So this is one operation, so I'm going to increment number of operations plus plus. For this is another operation, so I'm going to increment number of operations here also. And also this is another operation, so I'm going to increment number of operations plus plus. So if I run my program, so sum array, if I have an array with 10 elements and pass it to sum array, I have created an object of big O notation class. So using this class, I can this object, I can access the methods of the class. One of the method was sum array or sum arr, b.sum arr. I'm going to pass array 1 here. If I run it, okay, number of operation not defined. Okay, here I should access it through the get number of operations. Run it. So we can see the number of operation is 12 operations to execute this sum array function. But if I increase the input data size, say I want to increase it to 100, So the number of operations required to execute that this function or algorithm increases proportionally. So we get 102 operations to execute the element of this array. Say if I make it thousands, so the number of operations also increase by 1000. We get 1002 operations. So this is a linear time complexity. Then we have logarithmic time complexity, also denoted as big O of log n. It's basically a measure of an algorithm's efficiency where the time taken to execute the algorithm grows logarithmically with the size of data input. This means that as the input size increases, the time taken to run the algorithm does not increase linearly, but it increases more slowly according to the algorithmic function. So let's understand the logarithmic time complexity deeper. When we talk about the logarithmic time complexity in computer science, we refer to log base 2, a logarithm having a base 2. But in the case of general mathematics or calculus, when we talk about logarithm functions, we generally refer to log base 10. If we take log base 2 of n, or we say log of n in computer science, we basically mean log base 2 of n, where n is the input data set. As we can see, the graph of O log n, or logarithmic time complexity, as the input data set increases, the amount of operation taken to execute the function increases very slightly. So this is one of the best time complexities we can achieve. It's better than linear time complexity, and almost it resides between the constant time complexity and linear time complexity. So after the constant time complexity, logarithmic time complexity is the best one. So in this video, we will have a full understanding and intuitive understanding of what logarithm means and why it is useful for us when declaring a complexity using logarithmic time or logarithmic running time. So when I say log base 2 of 8, log base 2 of 8, what I basically mean here is the base is 2. To find out the answer to log base 2 of 8, as I ask myself what number should I raise this base to in order to get the number in the parentheses, in this case 8. So I can raise this base number to 3, so 2 to the power of 3 equal to 8. I get the number in the parentheses, or the given number or data set. In this case, log base 2 of 8 equal to 3, or in other words, we can write log base 2 of 8 as log base 2 of 2 to the power 3. So instead of 8, we can write 2 to the power of 3. So one rule of logarithm is that we can bring the power as a coefficient, so we can say log 3 log base 2 of 2. So logarithm of numbers with same base is going to be 1. So this is going to be 3 into 1. That's equal to 3. So log base 2 of 8 equals to 3. But where does this 3 comes from? It comes from the nature of logarithmic time complexity, which halves the input data set each time. When we say log base 2, it means we keep halving the given number or the given data set until we reach 1 or something closer to 1. In other words, we are asking how many times do we have to divide the given number, in this case 8, by 2 to get what? To the answer is 3. So I can divide this number 8 3 times by 2 to get to number 1 or closer to 1. So I can write 8 divided by 2 equal to 4 1 times. Then the result is 4. 4 divided by 2 equal to 2 2 times. 2 divided by 2 equal to 3 times. Sorry, this is not 3, this is 1. 2 divided by 2 equal to 1. So we basically divided the given number by 2 3 times to reach to number 1 or a number closer to 1. That's why we get this number 3 from. So in this case, we cut the input size in half 3 times. That's why a log base 2 or logarithmic time complexity is often considered the best running time complexity, as it reduces the input data size by half with each iteration. In other words, each time we divide the input data size by 2, we significantly reduce or decrease the number of operation or the time taking to execute the algorithm or the function. It's also worth mentioning that logarithms are the inverse of exponentiation, just as subtraction is the inverse of addition and multiplication is the inverse of division. To denote this log base 2 of 3, to denote or represent the inverse of this expression, we can use the exponentiation. We can write 2 to the power of 3 equal to, we know 2 to the power of 3 equal to 2 into 2 3 times equal to 8. So that's why we get 8. And the inverse of this exponentiation expression is going to be log base 2 of 8 equal to 3. So the general form is, if we have an exponentiation expression, say we have x to the power of z equal to y, to show the inverse of this exponentiation expression as a logarithmic expression or function, we can say we can take the base at x here, so we can say log base x of y equal to z. So this is the inverse of the exponentiation expression. Same as I said, in general mathematics, the base of logarithm is 10. Say I have 10,000. If I want to represent the logarithmic of 10,000, so log of 10,000 base 10 equal to, so what number should I raise this power by in order to get 10,000? So I can raise 10 by 4 to get this 10,000. So this is going to be 4. Or in other words, if I write the inverse of that, 10 to the power of 4 is going to be 10,000. So 10 is the base, and 10 is the base here, and the result of the logarithm is the power of exponent, or the exponent of exponentiation expression. We also know that 2 to the power of 0 is going to be 1. If we write it in logarithmic expression, we can say log base 2 of 1 equal to 0. We also know 2 to the power of 1 equal to 2. We can write it as log base 2 of 2 equal to 1. We also have 2 to the power of 2 equal to 4. We can write it as log base 2 of 4 equal to 2. We also have 2 to the power of 3 we saw equal to 8. We can write log base 2 of 8 equal to 3. We also have log base 2 of 16. So we have 2 to the power of 4 equal to 16. Also log base 2 of 16 equal to 4. Same case with 2 to the power of 5 is equal to 16 into 2 is equal to 32. Log base 2 of 32 equal to 5. So as we can see, as the input data size here increases from 1, 2, goes to the 4, to 8, to 16, to 32, each time the input data size increases or doubles, in this case, the number of operations required by a logarithmic time complexity increases only by 1. So if we make our data set from 16 to 32, we would need only one more operation to execute the function. That is why logarithmic time complexity is one of the best time complexities we can achieve. To better understand the logarithmic time complexity, consider an algorithm that divides the input in half at each time, such as binary search algorithm. So here I have a binary search function or algorithm that takes an integer array and also a target value of type integer. So it's going to search this array and find the target value. If the target value is found, it's going to return the target value. Otherwise, it's going to return -1. It's going to return, I think, the index of the target value. Okay. So this function runs in O log n of O log n, or logarithmic time complexity, because how it works is we take two pointers to the array, one at the beginning of array called left pointer and one pointer to the end of the array called right pointer. We check if until left pointer is less than or equal to the right pointer, we find the middle element of the array, or index of the middle element of the array. We check if the middle element equal to the target, we just return the index of that middle element. One thing to mention, that binary search algorithm only works with the sorted array. So this array should be sorted first. Okay, if the target is not, if the middle element is not equal to the target, what we are going to do, we check if the middle element is less than the target. If so, we ignore the left half of the arrays and we set the left pointer to the mid plus 1. Otherwise, we ignore the right half of the array and we set the right pointer to mid minus 1. So if we take a look at a sorted array here, this is a sorted array. What the binary search algorithm is going to do, it is going to first find the middle index or the middle element. In this case, the middle element is at index 4. So middle index or middle element is going to be at index 4. So mid index is going to be 4. Say we want to search for a target value that's 9. In the case of linear time, we would have start from the beginning of the array and going all the way up to the end of the array. That's going to take big O of n or linear time complexity to find 9. But in case of binary search, it has a big O of log n time complexity. We saw that log n means having the dataset, input dataset in each iteration. So each time we iterate over the dataset, we make it have that significantly decrease the number of operations required. So what we are going to do, we check if item at middle index is equal to the target. So we check if array of mid or array of 4 in this case equal to the target. If that is so, we just return the index value mid. Otherwise, we check if the element at the middle is greater than the target value or it is less than the target value. We check if array of mid or item at the middle of the array is greater than the target. If it is so, we know that the target element resides or exists in this part half of the array. We can ignore this part of the array. But if it is not, but if the target value is greater than the middle element, we know that the target exists in this portion of array and we can ignore this half of the array in the next iteration. In this case, 9 is greater than 5 here, so we know that that 9 or the target value does not reside or exist in this portion of array since array is sorted, so we can ignore this all element of array and our new array will look like that. Once we check if that array of mid is smaller or less than the target, so the target exists in the upper bound, what we can do is, previously we had a left pointer here at the beginning of the array and we had a right pointer at the end of the array. What we are going to do, in order to ignore this half of the array, we can move this left pointer to here, to this 5 index. So our new array is going to look like 6, 7, 8, and 9. So this is going to be our new array, and our right index or left index is going to point here. This is 5, this is 6, this is 7, and this is 8. So left pointer points here and the right pointer points here. So right now, again, we are going to find the middle element. So in this case, the middle element is, say, number 7 or index 6. So mid is equal to 6. We check if array of 6, if array of 6 is equal to the target, 7 is not equal to the target, 7 is not 9, equal to 9. So we can check again if array of mid, if array of 6 is greater than target, array of 6 which is 7 not greater than target, we know that the element does not reside in this portion of the array, so we just can ignore this and we move our right pointer here. Okay, again we are going to take the middle element, so our new array is going to look like this. We have 8 and we have 9. Say this time we take the middle element as 8. So this is going to be index 7 and this is going to be index 8. So the middle element this time mid is equal to 7. We again check if array of mid equal to target. No, it's not. Then we check if array of mid is greater than target. No. We know that the target does not reside in this portion of array, so we can ignore this portion of array and we move our left pointer to point here. So right now our array is going to look like this. We have only one element, right pointer points here and also left pointer points here. So we loop through until left pointer is less than or equal to the right pointer. So right now it's equal to the right pointer, it's true, it will go inside the loop, and we check if array of mid equal to the target. Array of mid, array of this is going to be 8 index 8 array of 8 equal to target. Yes, that is, we just simply return the mid index, which is in this case 8. We found the item or the target at index 8 in the worst case scenario. We saw in each iteration we have the number of elements that decrease the number of operations significantly. So at the first iteration we had a bigger array. At the second iteration we considered only half of the array, and third iteration our array became smaller and smaller. So in maximum in 3 iterations we were able to find the target value, which is 9 in this case. So let me show you this website's find log base2 of a number. If I have 8 elements in my array, in worst case scenario the maximum number of comparison or operations I need is 3. In 3 operations I can find the target value in a binary search tree or an algorithm with logarithmic time complexity. If I make the data set 16, in case of a linear time complexity I would need to do 16 operations or comparison, but in case of logarithmic time complexity, each time I double my data set, only the number of operations increases by 1. So if I make it 32, so I require only 5 operations. If I make it 64, I require only 6 operations. If I make it 1000, in case of linear search, I would require 1000 operations. But in case of logarithmic time complexity, I need only 10 operation maximum. If I make it 10,000, I may require only 13 operations. As we can see, if we drastically increase the input data set, the number of operation or running time increases very slightly. So if I make it like this much long data item, it is like millions of data set elements in an array. We require maximum 33, at most 33 operations to find the target value. Then we have quadratic time complexity. Basically, quadratic time complexity refers to an algorithm whose performance is directly proportional to the square of the size of the input data set. This is common with algorithms that involves nested iteration or nested for loop. It's denoted as big O of n square. So the rule of thumb is when we have a 2 nested iteration or 2 nested loop, that loops from 0 up to n, where n is the size of the array. So we know that it's going to be big O of n. So this iteration has iterates n time, and this also iterates n time. And since they are nested, we multiply that n into n is going to be n square. So as we increase the data set, say I have 1 element in my data set, so 1 square is going to be 1. I need only 1 operation. If I increase the number of elements by 1 and make it 2 elements, so 2 square is going to be 4. I require 4 operation, and if I make number of elements 3 square is going to be 3 square is going to be 9, and if I make it 4 square is going to be 16. We can see for each increase in number of elements, we can see that number of operation increases exponentially. Another example of a quadratic time complexity is when we have a 2D array and we want to process the elements of the array. We first get the number of rows of the array and also number of elements. So for each row, for n I equal to 0, I less than row or number of rows, we iterate over each column and process the element of the array. So in this case, this runs n times and this runs m times. So the time complexity of this algorithm is going to be big O of n into m, where n is the number of rows of a 2D array and m is the number of columns of a 2D array. Then we have, if we take a look at the graph of quadratic time complexity, we can see that the number of operations required increases drastically as the number of input size increases slightly. So then we have cubic time complexity, or big O of n cube. In this case, the time complexity refers to an algorithm whose performance is directly proportional to the cube of the size of the input data set. So cubic time complexity is denoted as big O of n cube. or in other words, if we have 3 nested for loops that loops from 0 to n, so each time each iteration or for loop loops n times or n iteration, so we have n into n into n, that's going to be n cube. This is one example of cubic time complexity. This kind of time complexity is often associated with algorithms that involves like 3 nested loops over the input data. As the size of input data increases, the time taken by these algorithms increases cubically. For example, if I have only one element in my data set, so the cube of 1 is going to be 1. I will need only one operation. If I have 2 elements, so 2 cube is going to be 8. I will need 8 operation. We can see for a slight jump in number of item, the number of operation jumps like exponentially. If I have 3 elements, so 3 cube is going to be 27. So we can see the number of operation or time taken to execute a cubic time complexity increases very drastically. This is not a good time complexity. So in summary, we learned about constant time complexity, which is big O of 1. This is smaller or take less time than linear time complexity or big O of n. Big O of n is smaller or takes less time than in the middle we learn about logarithmic time complexity. So big O of n, big O of log n, so big O of log n is going to take greater time than a constant time complexity, but big O of log n or linear logarithmic time complexity takes less time than linear time complexity or big O of n. Then big O of n or linear time complexity takes less time than quadratic time complexity or big O of n square, where big O of n square or quadratic time complexity takes less time than cubic time complexity, big O of n cube, and big O of n cube takes less time than exponential time complexity and factorial time complexity. So this was introduction to time complexity and big O notation. Thank you guys for watching and see you in the next video. Bye bye.